So we'll go on lecturing on algebraic groups, and I will talk about basic decompositions about concerning affine group schemes. So let me recall the general context. K is a commutative ring with unit. And G is an affine group scheme over K. Meaning that G as a functor is isomorphic to represented functor by some K algebra A, and we saw yesterday that the fact that it's a group, it values in groups, says that A has a very specific algebraic structure. A is a Hopf algebra over K, and we denote by delta the map corresponding to translating multiplication, S, epsilon, the map corresponding to the unit element, namely the injection of the trivial group in the values, in each value of this functor, and S, the map corresponding to inversion. Okay, so for it will be it's more intuitive to have a specific notation for A. We most of the time use KG for A in this situation. Okay, so I want to discuss decompositions, some basic decompositions. The first one consists in a connected component, and the second one will be a globalization of Jordan decomposition of matrices. So let's start with a connected component. Assume K is a field. For this part. Then recall that an algebra, a K algebra, is called étale. Okay, let's call it B. If for instance B tensor, the algebraic closure is a product, a finite product. Okay, so what we are going to do is to look for a maximal étale subalgebra in K of G in order to define a group corresponding to the group of connected components of the affine group schemes. different group scheme G. Okay. So let's start with, let's assume that G is algebraic over K, meaning that Kg is finitely generated. Okay, so then there is a maximal étale subalgebra in K of G. This comes from the fact that a product of two étale subalgebra is still an étale subalgebra. This notion is very stable. So we denote it by pi naught of K of G. And there are two nice properties, facts. For any field extension we have this commutation property, and it also behaves well with respect to tensor product. For any other finitely generated K algebra B, we have okay. So that's the algebraic part. So let's go back to group theory. We want to define connectedness by using this notion. We want to define connected components. For G. So when I say connected components, there is no topology so far. I'm anticipating on what on the use of Zariski topology, but it will correspond to this. So the first thing to do is to identify connected group schemes. Connected algebraic defined group schemes. This is done by the following result, proposition. Let G be an algebraic affine group scheme over a field K. Then the following are equivalent. First, the maximal étal of subalgebra is trivial. Then I use the Zariski topology on the spectrum of K of G. And this can be rephrased in two close ways. First, the spectrum is irreducible. And because we have a group structure involved, this is equivalent to the fact that actually it is connected. The last thing is again algebraic. If you mod out by the nilpotent element, you get an integral domain. Yeah. Sorry? Yeah. It's a. Yeah. Sorry. Yeah. Thank you. Okay. Okay, so this is the first step, and then to define the connected component, one starts by defining the group of connected components. So in general, general means under these assumptions. Start with the inclusion of the maximal étal of subalgebra into the regular functions. This gives rise to a map. Sorry, denotes the group associated to this étal algebra by phi naught of G. Then the map, the above map gives rise to a morphism of affine group schemes. Okay, so this is what we have first. And the decomposition result is as follows. So by definition, a group is étal if it's an affine group scheme is étal. is called étal. If so is it's of algebra. So now I can state the decomposition result. Any map any morphism from G to an étal group scheme factors through the map from G to pi naught of G. The kernel of this map is a closed normal connected subgroup in G. We denote it by G note. And the last point is that this the constructions of the group of connected components and of the connected component itself, of the identity component, commute with field extension. Okay, so this is the first decomposition result I wanted to. Yeah. Yes. Yes, it is, because you can use you have this. You can go the phone. Yeah, sure. No. What you can attach to such an algebra is what does it? Sorry. So what you can. Let me see. Yeah, it is, but I'm sorry. I have to. Yeah. Sorry. Okay. Okay, let me now go to the second kind of decompositions, namely a Jordan decomposition. Okay, so let me recall this decomposition at the level of a matrix. So let's fix N, and let K be a perfect field. Okay, sorry. So now I'm starting with a matrix. And Jordan decomposition can be phrased this way. There exists two elements, GS, GU, two matrices, such that GS is a semi-simple, GU is a unipotent. These elements commute. And G is the product of these two matrices. The couple of GS, GU is uniquely determined by these properties. And in fact, any element, any of the two factors belong to the subalgebra generated by the matrix we started with. Okay. Okay, so I simply want to explain. So when the characteristic sorry, yes, Jelen. Okay, so what's the point? So when the polynomial characteristic is split, the characteristic polynomial is split, then this is basically arithmetics of polynomials. This is basically proved by a tricks. With of arithmetics of polynomials. You use a Bezout in several ways. And the point is where I simply want to explain why a perfect comes into play. So what you obtain is a product GD times GS, where D is diagonalizable. And the point is that you then, in the general case, use a Galois action. Use the Galois action. And this is why you need a perfectness. So you combine the gain reaction and the uniqueness statement in the split case. Okay, so this is the starting point of the second decomposition. So the next point, which is consists in prescribing a closed subgroup in GLN, picking an element in this closed subgroup, and checking that the components, the semi-simple and unipotent components, stay in the closed subgroup. So that's the next thing. If G is a closed subgroup in GLN, then still assume K is perfect. Then for any G in G of K, the component GS and GU belong to G of K. Okay. So now the point is to globalize this, and this is doable if you assume that the group, the affine group scheme G is abelian. Then you have the decomposition for the whole group. This is the theorem. Let G be an affine group scheme over some perfect field K. Assume G is abelian. Then G can be written as a direct product. Where the first factor is diagonalizable over Ks, and the second factor is unipotent. Okay, so I stated it, if you are a bit careful, you see that I stated it for a affine group scheme over K, which is a bit delicate if you want to define what is diagonalizable and unipotent. But in the algebraic case, it simply means, well, you know that since yesterday we know that in an algebraic affine group scheme is after all a group of matrices. So I will not write anything here, but you can say that an algebraic, one definition for a unipotent algebraic group is the fact that any matrix contained in it is a unipotent matrix, meaning that, okay, so when at least when G is algebraic over K, then GU so is GU. And definition of a unipotent group is simply the fact that any element, any matrix in this group is unipotent. Meaning that G minus identity is nilpotent. Okay. And the same for semi-simple. But still, the statement makes sense in an affine group scheme, which is not necessarily algebraic, but you have to adapt these two definitions. I won't go into details. But for instance, unipotent simply means that for any linear you have to adapt the definition of a the global definition of a unipotent group, and the one which is okay in this case is to say that whenever you act on a vector space, you have a fixed vector. This is the right definition of unipotent when you're not algebraic. Okay, this is the detail. And let me now go to differential calculus. So I want to explain that in the case of Hopf algebras, the module of differentials can be described explicitly. So I want to do two things. First, describe the module of differentials for a Hopf algebra, and state some well-known consequences in characteristic 0. Plus Cartier's reducedness theorem in characteristic 0. And then I want to introduce the Lie algebra and the adjoint representation. Okay. Okay, so again, let's start in the following situation. K is a ring and A is a K algebra. I will quickly recall the general setting. Recall that a derivation, a K derivation of A is a K-linear map which satisfies to some A module. M is a K-linear map D from A to M, which satisfies Leibniz identity. So the remark is that if we, in the very special case, in the special case, where A is, say, let's call it A tilde for what follows. If we start with an algebra of polynomials, then a derivation is completely characterized by the images of the variables, the canonical variables. By the images of the variables xi's, and conversely there is no condition on the choice of these images. Of the choices of these images. Okay, so in other words, we can, if we denote by der k AM, the space of derivations from A to M, then this space is isomorphic to, in the polynomial case, and this is isomorphic to m to the n, which is nothing else than the homomorphism from the homomorphism of A modules from A tilde to the n to n. Okay, so the general case is the following. Proposition. There is a unique, there exists a couple omega A dA where omega A is an A module and dA is a k derivation. Such that for any k derivation d from A to M, there exists a unique map phi, morphism of A modules, such that D is 5 composed with dA. Okay, so let me So let me recall the proof in order to be, in order that, well, to see that it's not it's quite it's concrete algebra. So the easy case was done before the statement. It's when A is A tilde, then you can take, let's be more precise. You can take omega as the direct sum, sorry, tilde, the free A tilde module of rank n, where here this is simply a symbol so far, and it becomes the image of xi when you define the A tilde. Okay, so this works in this case, and in the general case, you write A as the quotient of some A tilde by an ideal E, and you define a set, define omega A K to be the previous module of differentials modded out by the ideal, the submodules generated by the ideal, plus the submodule generated by the image of the ideal E by the derivation. Okay, so this is quite standard. Okay, we have this map. And actually you can factor this map through this one to obtain the derivation here. Okay, so then what you can check that if A to M, if D from A to M is a K derivation, then compose with the map from A tilde to A to obtain a tilde a k derivation from a tilde from the polynomial ring, and check that the so obtained couple works. Okay, so this is a bit. So I recall this in order to show that in the Hopf theoretic case, things become much less become less abstract and can be described concretely in terms of the maps given by the Hopf algebra structure. So now we assume that A is a Hopf algebra over K. Then again, since this is a much richer structure, which is, so to speak, heavy when you want to describe the structure, but then you can, the counterpart is that you have some simplifications when you describe classical objects such as the modulo differential. The result is the same, so sorry, I have to introduce some objects. Let I be the kernel of the map epsilon from A to K. So an element X in A can be written as follows. Where Y belongs to the kernel of epsilon, and we have a map, we have a projection map, the map from I to I mod I square, which is the classical thing one considers when doing differential calculus at a given point. Now here's the statement. Let A be a Hopf algebra over K. Then we can identify the module of differentials. It is isomorphic to the tensor product of A with I mod I square. And the derivation is given by is defined as follows. If A start with an element in A, write it. You need to write it to introduce its image by the co-multiplication. And dA of A is simply the sum of the tensors is the sum of these tensors, where pi is defined where pi is the extension of the projection from I to I mod I square, given by Okay, so this is the concrete description of the module of differentials when you're dealing with fine group schemes. And the fact that it is, so in particular it says that it says that when you're working over a field, because this is a ring so far, when you're working over a field, this is a k-vector space, and the module of differential is a free A module. Okay. This is already something, but the nicest thing is when you specialize to the case where K is a field and is of characteristic 0. Okay, so this is 2, 8, 3. Characteristic 0. Then this is the so-called Cartier theorem, which tells you the following. Let A be a Hopf algebra over some field K of characteristic 0. Then A is reduced. So one consequence will be that any a fine group scheme over some field of characteristic 0 will be smooth. This is actually proved by a computation which are quite elementary, very clever computation, but it's the proof is quite elementary. Okay, so this is enough for abstract differential calculus. I want now now to go to what's a very useful tool in Lie theory in general, which is namely the use of the tangent space as the unit element, which are called Lie algebras. And I promise that not so many things would be functorial after yesterday, but in that specific case of Lie algebra, it's very useful to use functorial. I want to finish today's talk by explaining that the functorial point of view for algebraic groups is very useful when you have to deal with Lie algebras. So what I will do is to define Lie algebras in a quite a standard way, and then present the functorial point of view on it, and compute some Lie algebra by very simple arguments, thanks to group functors. Okay, so let's go. Lie algebras, Lie algebra, and a joint representation. Okay, so let's first define the Lie algebra. So we start again with a G, define group scheme over K. So A is the representing algebra. So we want to introduce, classically in Lie theory, the Lie algebra is defined as the tangent space at the unit element. What we will do is to define it as an invariant derivation. An element of a Lie algebra will be a derivation which is invariant under translation. So classically, the Lie algebra of a Lie group is the tangent space at the identity element And then once you have done this, you have to work a little bit to explain how to define the bracket. Because so what we do in this context is to start with a point of view which allows you to define the bracket quite easily. Wait. Definition. The Lie algebra E of G is the set of left invariant K derivations It is a K vector space. It is a K module. Together with a bracket map. Which is K bilinear. skew symmetric. And satisfies the Jacobi identity. Well, actually, the bracket is given by Okay, so what I have to do now is to explain what is the left invariant derivation. Okay, this is not completely clear. So this definition requires some explanation. Okay, so let's let T be a K-linear map. We want to say what it means to be invariant under translation. So we have to define the translation. So recall that the product in the group G, okay, the product in the group G is given by delta. Namely, more precisely, for any G and X in G of R, for R a K algebra, G times X is given by this formula. Okay, which means that so what is translation by G? This is simply what you obtain when you fix G and you let X vary. So when did you see from this that left translation by G is described by the formula this is an element from okay, so we define we say that T is invariant under left translations if we have if they commute. If it commutes with any translation. Okay, so let's compute these two parts. And we want this for any g. So if now we want to forget g, this simply means this can be stated as follows. T is a left invariant if and only if delta t is equal to identity tensor t composed with t. And this is a short way, a bit abstract, but a short way to encode the fact that a K-linear map is invariant under left translation. So to sum up, to go back to Lie algebras, we can describe the Lie algebra of G, more precisely with respect to the definition, as a set of K derivation from A to A. Such that we have this equality, this commutative diagram. Okay, so this is still a bit formal, but from this point of view, you can check that, for instance, if you compose you have to check some details, for instance, to check that when you compose, when you take the bracket of a left invariant derivation, you obtain a left invariant derivation. But now, what I want to do is to, as I said, explain that if you use the functorial point of view, you can compute easily some Lie algebras. Okay, so let G be an affine group scheme over K. then the following spaces are following K modules are isomorphic. First, the Lie algebra of G. Then the K derivation from Kg to K, which is the classical Lie theoretic point of view. It's exactly the tangent space. And then the interesting point for several questions, namely the kernel of the map corresponding to, let me write it, of a group homomorphism given by evaluation of G on a certain on a specific map. So what is this ring? What is this this K algebra? It is simply the algebra of Cartier numbers, where tau is a class of X. Okay, so in the group case, you can compute the Lie algebra in this way. And you can recover the full structure of the Lie algebra from this point of view. Okay, let me write some example. If you start with SLN, which attaches to any K algebra R, any ring R, the group of matrices of determinant 1. Okay, so what does it mean to be in the kernel of this map? It simply means that you can be written as, in this case, at least, it means then you can be written as an element of the form identity plus a perturbation tau plus a matrix M, right? Okay, so an element in the kernel of this map can be written as identity plus tau M, where M is any matrix with coefficients in K. So now go back to the formula for determinant. Use the formula in this case, you can check that for such a matrix to have determinant 1, whenever you have two toes in this product, the term disappears. So in some sense, almost everything disappears. What is left is only two terms. Oh, sorry. So apply this to this matrix. Then determinant is equal to 1 plus tau times the trace. So okay, we used quite an abstract way to define the Lie algebra, but eventually what we obtain is a functorial. The functorial point of view turns out to be, in many cases, the most the easiest way to compute the Lie algebra from the algebraic point of view. And this way you recover the identification between the Lie algebra in the usual sense and the algebra in the functorial way, is that the Lie algebra is given by the matrix coefficient in front of tau in this infinitesimal writing. And you recover this way that the Lie algebra of SLN is the space of traceless matrices. Okay. Also, if you consider the, so let's, you can also consider the orthogonal group. Then if you replace G by, if you do it more quickly, if you replace G by matrices of this form, then this equation translates to this equation, if you're only interested in the coefficients before tau. Right. Sorry. Actually, the bracket can also be computed this way.
Let me go back to the example.
Yeah.
So the kernel of the map is just those matrices of that form, right? IN
Yep.
plus L, which corresponds to number 3, right there. Right?
Yeah, exactly.
So how do you get trace 0? So a general member of the kernel is just any M, right?
Yeah.
And then I understand
So you compute.
I understand that the determinant count. The determinant is 1 plus tau.
Yeah. And then you want the determinant to be 1, so it means that what you have in front of tau has to be 0.
Yeah. You want the determinant. All right.
Okay, so what I wanted to say to so the point is that in this case, the Lie algebra can be seen as a subgroup, actually, a normal subgroup. Okay, for the bracket. Functorial point of view shows that it can be computed by means of commutators. So again, I check it. I will simply check it on matrix groups. If you're given two elements, sorry. In Lie algebra. Then you compute the commutator, and what is a bit bothering in this case that you have the same notation for commutator and Lie bracket, but you will see that it's not very harmful. In the sense of commutators. Then what survives in this case? I will write it. So the inverse of such a matrix is easy to compute. This is simply because U square is 0. The inverse is given by this formula. N. Okay, and what you obtain is simply this formula, which is the usual Lie bracket on matrices. Okay, so I check it on matrices. This is I give kind of recipe. The point is to not to give the same name to the infinitesimal element. And what the functorial point of view says is that you don't have to understand much the algebra of the Hopf algebra. In some cases, it's you can compute the Lie algebra and the bracket simply by matrix computation with a nilpotent element, a specific nilpotent element introduced in the computation. So last thing is to define the adjoint representation. Okay, so this is 2b4. So what is the adjoint representation in the context of Lie groups? It's simply considering conjugations by an element. You fix an element and you want to, so it's sorry, I should start by saying that this is a linear representation from G to the linear transformations of the Lie algebra. And usually it's given by differentiating conjugations by an element. Okay, what you want to do in the Lie group context. Add of G is simply the differential at the identity element of conjugation by G. Sorry, small g. Okay, so in this context, in the algebraic context, we can use the fact that so in some sense it's an infinite, it's the adjoint representation tells you what conjugation do, what conjugations do at the infinitesimal on the infinitesimal part of the group identity element. So here we have this computation show that we can concretely use the infinitesimal part by introducing this nilpotent element. So the trick is the same. We can use the fact that the Lie algebra is a normal subgroup in this group. Conjugation by any element so conjugation by any element in G of K stabilizes Lie of G, and this is exactly the adjoint representation from this point of view. Okay, so you don't have to, in some sense, differentiating corresponds to the fact that you're only interested in the infinitesimal part of the group G of K of tau. And this is the Lie algebra from this point of view. And in many cases, it's the simplest point of view to compute the adjoint representation. What I didn't say in the same spirit is that, again, since you can see the Lie algebra as a normal subgroup in some group with infinitesimals, allows you to deduce that from any map between two affine group schemes, you can deduce a